Our second video will address organic chemistry functional groups. And these obviously will change the names, and it also changes the chemistry of the organic molecule. So here are all the functional groups that, yes, you need to know. And I'm sure you have a picture of this in your textbook. The first couple of things on there just review alkane, alkene, alkyne, and then we actually get into the functional groups, which we will address one at a time. So what I want you to notice is the compound name, and there's alcohols, ethers, aldehydes, ketones, carboxylic acids, esters, amines, and amides. And then you've got the basic functional group. Now, if you look at this data table, you're going to see an R on each of these. Guys, R is not on the periodic table. R just says something hanging off the other end. It could be a chain of 100 carbons. It could be anything over there. But if you've got a bunch of carbons and then on the end, OH, it's an alcohol. And you can see that in that example. There's a bunch of C's and H's and then OH is sticking off on the end. Remember, be careful with OHs. OHs could be an alcohol, could be a hydroxide, it could be a base, and it can also be a carboxylic acid. So you have to be really, really careful when you're identifying these things. So we're going to look at each one of these in turn. Each functional group undergoes the same kind of reactions in every molecule, regardless of how big or how complex it might be. And again, to simplify, we often shorten it with an R, and that R just represents whatever that carbon chain is hanging off. It could be a methyl, could be an ethyl, it could be something with hundreds of carbons. We just shorten it to make it a little bit easier. So one last time, you guys, R is not on the periodic table. R is not an element. It just represents something. Let's look at alcohols to begin with. These are compounds that have one or more hydrogens that have been replaced with an OH group. And we call that a hydroxyl group or an alcohol group. Either one is appropriate. And you change the ending of the name to OL. So ethane becomes ethanol. OL is how you know you have an alcohol. That OH is polar, so it participates in hydrogen bonding. It allows it to be soluble in polar solvents. The location of the OH sometimes needs to be pointed out, so you might have to say, like 2-butanol. We need to state where that OH is. Little FYI, the alcohol or the boiling points of alcohols are higher than alkanes because we have some polar bonds going on. We have some hydrogen bond going on. So those alcohols like to stick together a little bit more than your plain alkanes. So ethers are compounds where you have two hydrocarbons bonded to an oxygen. Do you see that oxygen right there? You've got a carbon chain on one side, a carbon chain on the other. And this is going to be silly, but how do I recognize this group? Either or. I don't know why, but I see that O in the middle and I think either or. Ether, either or. You've got an O in the middle and something on either side. These can be formed from two molecules of alcohol by removing a water. You can also, by the way, when you remove water, it's called a condensation reaction. But here's just several different examples of ethers. On all of them, you should be able to note that oxygen in the middle with some sort of hydrocarbon on the other sides. So let's look at aldehydes and ketones. Both contain the carbonyl group C double bonded to an O. And if you look at any of those molecules, you see that C double bonded to an O. Aldehydes have the carbonyl group and at least one H attached. Common examples would be vanilla and cinnamon. Ketones, though, they have the carbonyl group in the interior of the carbon atom so that it's surrounded by other atoms. Acetone is a really good example of a ketone. We use that to remove nail polish. Aldehydes are going to change the ending of their names to AL. Ketones change the ending to ONE. And some molecules have more than one functional group, for example, testosterone there. But usually one of the groups has the more predominant chemistry. So if you look again at the ONEs, these are ketones. You're going to see that CO group in the middle versus an aldehyde, the CO is always on the end. And there's your difference between ketones and aldehydes. Carboxylic acids, we've seen these a lot this year. And these are written as a COOH group. I know we say it like that, but really what you should see is that it's a C double bonded to an O with OH. And remember, because of this O right here, it's pulling all the electrons up toward it, and that leaves that H on the end very, very positive, which is why it's an acidic H. And here's just a bunch of different examples of carboxylic acids. Notice we changed the ending to OIC. And some of them, like citric acid, it just has its own common name. But formic acid is actually methanoic acid. Well, you should recognize meth in there. Meth means one carbon. So we have one carbon with that COOH group, so it becomes methanoic. Again, this is probably one of those groups where you see a lot of both traditional names like methanoic acid, benzoic acid, and then they also have their own name, the more common name. Esters. They're not ethers, they're esters. And you're going to notice that you've got the C double bonded to an O, but you also have an O there. So it kind of looks like some of the other functional groups put together. Well, in reality, what these are is you have a carboxylic acid where the H has been replaced with a carbon-containing group. Do you see right here the COO group? There's just no H. Instead, we slapped a methyl on there. So you do have a carboxylic acid kind of hiding in there. But the name is a little bit complicated, and we'll practice this in class. It comes from the alcohol followed by the name of the group that contributes the carboxylic acid. And then we do a little bit of replacing. So if you look at this ugly formula here, okay, this piece right here was an alcohol. And so it's an ethyl alcohol. And then this right here has 4 carbons. So that's your butane. But it was a carboxylic acid, right? So what you do is you start with the second half, ethyl, and then instead of butanoic, we change it to butyrate. These are a little bit complicated. We'll practice them a little bit, and you're just going to have to memorize. Just a little bit more on esters. Because they're made up of an alcohol and a carboxylic acid, we can add a water. We call that hydrolysis, meaning to split using water, and we can actually get those two things back. When you use a base, we call it saponification, because sapon means, or however you say it, I have no idea, it means soap in Latin. Naturally occurring esters include fats and oils, which is why animal fat is boiled with a strong base to make soap. Another functional group are the amines and the amides. Let's talk about the amines first. Amines are where you have an NH3 group, but one of the H's has been replaced with an alkyl group. And what do I mean by that? Like you remove an H and you slap on a methyl. These are organic bases. They're Lewis bases. And amines can easily be turned into amides via condensation reactions. An amide contains the C double bonded to an O group attached to an N. So they're similar but different. And again, the amines are organic bases. The last thing we're going to talk about in this brief PowerPoint is chirality. Chiral means that you have two molecules. Like look at the example. They look like mirror images. I mean, they are mirror images, but if you actually took one and placed it on top of the other, they're not superimposable. Just like I just did with my hands. If you drew a line down between my hands, they're symmetrical. Well, except for my bent fingers from the rheumatoid arthritis. But if you superimpose them, they're not the same thing, because here's a thumb, here's a thumb. And that's what we're talking about here. But how do you recognize chirality or chirality? Yeah, that's right. What you do is you look at your whole molecule and just look at one carbon. As long as there are 4 different things attached to that carbon, there's chirality at that point. And then you move to the next carbon. So let's say this carbon's got CH3 over here, some giant chain of carbons, an H and an H. That is not chiral because there's not 4 different things around that carbon. So we'll again go over this in class together and we'll work on it together. Just little interesting points about it. They normally do have the same properties unless placed in a chiral environment, and these can be used to rotate the plane of polarized light, and a lot of drugs are actually dependent upon the chiral compounds. Now, if you notice in this slide, one is called S-alanine and one is R-alanine, and the weird thing about pharmaceuticals is sometimes the R will have more benefits than the S. Kind of odd.